In my last video, we used a circuit where we had an inductance and a frequency such that our inductive reactance was 5,000, our capacitive reactance was 8,000, and so it was a series circuit. So we had a real and imaginary part. Works out to be 3,000 minus 3,000, and this is what it is in polar. Now, instead of everything being in series, I put everything in parallel, same values. And so what we want to do is find the current coming out of the source here. Now what you can do is, since this is a parallel circuit with three components, you can find the individual currents, because you know you have a 10 volt drop, a 10 volt drop, and a 10 volt drop, and then add those currents up. The wrinkle in AC is that these currents are not going to be in phase with each other, so they will mix, sort of like we added up the resistances or the impedances last time when they were in series. You would now add up the currents as complex numbers to get the total current. In DC, we learned that the parallel formula for three resistors in parallel is 1 over RP equals 1 over R. 1 divided by RP equals 1 over R1. It's hard to type. Plus 1 over R2, etc. Plus dot dot dot. However many R's you got. The symmetry in electrical is the impedance formula is the same. So if I have impedances, in other words, I've got capacitive and inductive reactances, I can look at it in terms of the individual impedances. Now, a resistor is also an impedance. An inductive reactance is an impedance. So that'd be Z2, and then we'll just do the plus dot dot dot. There we go. So it's the same formula, except now in AC you have these angles. You have something that is different, or you have vectors, and the vectors are pointing different ways. In DC, these were vectors, but they all point in the same way, so the angle was always 0. Here the angle can be plus 90, minus 90, can be a mixture, can be 0, can be whatever. So basically you've got a window here of angles. And you have to resolve that in AC. That's what makes AC a little bit tougher than the DC. DC, you get the concept down. AC, you go in and you revisit a lot of it, but this time in terms of vectors. So, since everything is in parallel, and I know it's impedances, I can have Scilab come up with the values. So I've got three things in parallel. So I'm going to be 1 over, because ultimately I want the reciprocal of the 1 over Z1 plus 1 over Z2 plus 1 over Z3. So I'm doing 1 over opening, and my first component is a resistor, which is just its value, 3,000. So this is 1 over 3,000. So this would be my Z1. It's just a resistance. It's just like what we would have in DC. And then I'm going to do a 1 over. Now our middle term was an inductor, and our inductor value was 5,000. So it's also inductive. So what I have to do is I have to put my denominator in parentheses and make it an imaginary number. 5,000 times percent tells Scilab that the next number is its constant. So it has I defined. It has the imaginary operator defined. If you did it as angles, this would be 3,000 angle 0. This would be 5,000 angle 90. If you were doing it in a calculator and you were entering it in polar. Now I got to do the capacitor the same way. It's 8,000 and it's capacitive, so it's in the minus I direction. Times percent I. Now you may ask me, how do you know what direction they're in? Well, if it's purely resistance, there is no I. If it's inductance, it's positive I. If it's capacitance, it's negative I. That is not going to change. Once you get that down, you've got it. So what I've done is I have put it in the parallel form, just like we would have done for a DC circuit, except now I'm using imaginary numbers, and I'm going to let Scilab do the hard work. And it tells me that I come up with 2855 and 642I. Now, without doing the calculation, without doing the currents, and then finding the total current by adding the vectors, and then coming back out to the impedance, I don't see how you can intuitively come up with this number. I just never have seen that. It's always been one of those you have to crunch, and you have to crunch it correctly. So I'm 255 plus 642. So if I want to know what that is in polar, or you did it on a calculator, we can convert, because we have set that up and then we have forgot it. 2855 642. Okay, so my real is 2855 and my imaginary 642. I did notice the sign, it was positive. So my magnitude is 2926 at an angle of about 13 degrees. And what I should do is go in here and change these formulas to round to the nearest whole number is what I should do. Maybe this one and this one as well, because I can easily do that. So that would be my resistance, or my impedance, my total impedance. This is the rectangular form, this is the polar form, and in case you have forgotten already, all it is the triangle. So there's my magnitude. I think I can slide that over. Maybe. There we go. There's my magnitude and my angle. So that'd be 2926 at an angle of 13. And I can also get to the same point by going out 2855 and then up 642. So I'm going to this point starting from the origin. Just two different ways to get there. Okay? And you want to get to the skill that if you can get one, you can get the other, and you can go back and forth, because that's an important thing to be able to do. Okay, so now what was I going to do? Oh, we're 10 volts. So this is my impedance. So what I'm going to do is I'm going to say ZT. Actually, I'm going to up arrow, and I'm going to define this as ZT. And I'm going to do equals. It's going to do the same calculation again, but instead of calling it answer, which repeats or it writes over, it's going to call it ZT, which it won't write over. So you've got that in the memory of Scilab while you've got it open, while you're running it. Now I want to know I total. And from Ohm's law, I total is my V, which is 10 volts. The angle on the voltage is usually 0. There will be very few cases where it's not, but if you don't see an angle, you assume it's 0. So it's 10 divided by, and then instead of typing out that whole imaginary number, I can just use its variable, ZT. So this is my current, 3.3 0.75I, and it's minus. And these two numbers will be similar to these. So your current will have the opposite angle. So if your angle here is positive, your current will come up negative, same angle, as long as your voltage is 0. So I've got my current. So let's remember that, and we'll go to LT Spice, and we should just be able to tell Spice to solve it. And my current comes out to be 0.0034167 at an angle of 167. Okay, well, 167 is about minus 13. Because if you think about it, if you go around 167 and then you go 180 back the other way, you're at minus 13. That's something that you need to work, that you need to see a little bit. So don't worry so much about the phase angles, worry about the magnitude. So 3, 4. So if we go back to Scilab and my spreadsheet, now I've got the rectangular and I want to make it polar. So whoops. Okay, I'm going to delete those. And 0.0033 and minus 0.00075. Okay. So I go here and I do 0.00333 and then minus 0.00075. And you see I get about 3.4 at an angle of minus 12 or minus 13 degrees, which is exactly what I'm getting here for the total. Scilab, if you go through and do the calculation, each of the voltages, what it's doing is it's coming up with that and then it's adding it. And as you can see, it's not a pure add, because in polar you get this current added to this current added to this current, and you don't get this because of these angles. The angles matter. If you convert these all to rectangular and you add them up, you'll get what I got, rectangular. So sometimes it's easier to work in polar, sometimes it's easier to work in rectangular, depending on what you're doing. So I hope you get a sense of what's happening there. And I think we are good. And I thank you for watching.